This video covers section 1.2 and here we're gonna use pages, I think it's 11 through 14 in the note-taking guide. So here we're going to talk about function behavior and end behavior. So the first, I guess, category that we're going to talk about here is the direction of a function. Okay, so for what we're going to look at, we're going to have three cases. The first case is if a function is increasing on an interval. All right, so if you think about increasing as you move from left to right, when the inputs are increasing, the outputs also increase. So here you're going uphill as you move from left to right. Okay. Conversely, when you're decreasing as your inputs increase, so as you move from left to right, the outputs decrease. So this would be when we are going downhill. All right. Now, if a function is constant, that means it is not changing. It's neither going up nor down. So if we have a constant function, this is going to look like a horizontal line. It's completely flat. All right, so I don't think those concepts are new to you: increasing, decreasing, or constant. All right, now what might be new to you is thinking about curvature. All right, and the definition that your book uses is a little limited, so we're going to expand on that. But when you're thinking about curvature, if you're concave up, well, the definition your book uses is that it opens upward. Well, that's a little redundant in that you're using the, up in the definition as well. But concave up, if I think about something that's concave up, it might look like this. All right, so the opposite there would be concave down. So if you're concave down, well, the definition your text uses, it opens downward, which I don't think is stellar, but that might look something like this here. All right, now I want to expand on this definition slightly. So there are four cases that we're going to have for concavity. All right, and if I think about a circle, the four quadrants of it. And then I take this circle and I break it into four quadrants. All right, these are going to be the four cases of concavity that we might see. All right, so when I'm concave up, if I take any 2 points on the interval and connect them, the secant line, or the line that connects those 2 points, should be above. So in this case right here, if I take a point here, a point here, and I connect these two, do you see that that would be above the curve? All right, so that is my clue that this is concave up. Okay, so similarly, this quadrant over here, if I take any 2 points on this and I connect them, do you see that that black line again is above the blue line? So this is going to be concave up. Okay, now if I think about this first case over here, do you see I'm decreasing because I'm going downhill as I move left to right, but do you see I'm slowing down? So this case is when I am decreasing, but I'm decreasing slower. Okay, now over here in our second case, here if I move left to right, I'm going uphill. Okay, so I am increasing, but you see it becomes more and more steep. So this is the case where we are increasing. but I'm speeding up faster. Okay, so now let's look at the two cases where we might be concave down. So if I take 2 points here and I connect them, do you see that that black line is below? All right, so that tells me we are concave down. Okay, so similarly over here, if I take 2 points and I connect them, that black line is below the curve. So I am concave down. Now, here in the first case we looked at when we're concave down, I'm increasing because as I move left to right, I'm going up. But this is increasing, but it becomes less steep, so I'm increasing slower. Okay, over here where I am decreasing as I move left to right, okay, but you see it becomes more and more steep, so this would be where we are decreasing but faster. All right, so perhaps that these 4 cases might help you, or if you think about drawing a secant line that connects 2 points, if that line is above, we're concave up. All right, so here if I take 2 points and connect them and that is above the curve, I am concave up. And if I take 2 points on the interval and I connect them and that is below, I am concave down. Now, on a graph, if there's a point where I switch from concave up to concave down, or from concave down to concave up, that is called an inflection point. Okay, so for example, let's say I have something that looks like this. On the left part over here, I am concave down. All right, and on the right section over here, I am concave up. Okay, so this point, somewhere around right here, where I switch from up to down, is called an inflection point. All right, so let's see if we can identify whether each of these graphs are increasing, decreasing, or constant, as well as concave up or concave down. All right, so for this first one in the top left, if I move left to right, I'm going uphill. All right, so that is increasing. All right, and then if I take 2 points on this curve, maybe this one and this one, and I connect these two, assuming I can draw a straight line, that is above my curve, so this is going to be concave up. Alright, now next, if I go left to right here, I'm going uphill, so this one is increasing. And if I take 2 points on this curve and connect them, that secant line is below. Alright, so this is going to be concave down. Alright, over here, when I move left to right, I'm going downhill. So this is decreasing. Alright, and then when I connect 2 points here, I am above, so that is concave up. And lastly, here when I move left to right, I'm going downhill, so this is decreasing. And when I take 2 points here and connect them, that is below. Alright, so I am going to be concave down. Okay, for this example, the output right here, this is my output. W of t gives me the number of 1,000 20 to 24-year-olds that are working full time. And then my input down here is the number of years after 2001. So the number 1 would represent 1 year after 2001 or the year 2002. Okay, so state the interval or intervals in which the graph is increasing. Alright, so when I'm increasing, that's when I move from left to right, I'm going uphill. So if I start off here at 0, I'm going down, 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 so that's not it. Alright, then starting at 1.7, I start going up, 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 all the way to 5.6. Alright, so the notation I'm going to use for that is 1.7 is less than t, which is less than 5.6. Okay, some of you guys might have learned a different notation. You might have used a parenthesis to show that the 1.7 is not included, and then you use a 5.6 and then another parenthesis here. Alright, a parenthesis as opposed to a bracket. I am familiar with both notations and will accept both, but just know that on the WebAssign homework uses this less than notation. Alright, so next we want to know the interval or intervals in which the graph is decreasing. So that's where I'm going downhill. So in this case, at 0, I start to go down, 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 down here. And then again at 5.6 to 7. Alright, so we would write that 0 is less than t, which is less than 1.7. And I have a second one over here, which is 5.6 is less than t, which is less than 7. Okay, and again, if you're more familiar with the other notation, you might say 0 to 1.7. Okay, and then you have a union symbol, and you would say from 5.6 to 7. Okay, I will accept either, but from here on out I'm going to stick with this notation over here because that is what your online homework is going to show. Alright, so next I want to find where I am concave up. Okay, so the interval where I'm concave up is going to be where all of those segments are above the curve. So do you see if I take 2 points here and connect them, I'm above. Alright, here I'm above, I'm still above, up until between 3 and 4. And then over here I am switched to below, 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 below. Alright, so over here I'm concave up, over here I'm concave down. Alright, so the interval where I'm concave up would be from 0 to, we're going to estimate this is about 3.5. Okay, and that's just an estimate. We won't know how to find that exactly until close to the end of the semester. The interval in which I'm concave down, then, that would be from 3.5 to about 7 there. Okay, now, and then we want to estimate at what input value would we have an inflection point. So this is an estimate, remember, and the spot where we switch from concave up to concave down is somewhere around here. So we're going to estimate that to be about, right? Do you understand my squiggly equal sign here? Means that's just an estimate. We don't know for sure. This is about 3.5 would be the input value. Okay, so we've got increasing, decreasing, concave up, concave down. Now we want to talk about end behavior. All right, so the end behavior is not difficult. What gets a little cumbersome is the notation here. Okay, so the end behavior is what happens to the output as the input either increases forever or decreases forever. Okay, so if my input increases forever, we're going to be going to the right. Okay, now if I'm going to the right, I have 3 options here. Let's see if I can draw this. All right, so let's say I'm looking as my input increases forever. Well, if I increase forever, I could go up. Okay, I could level off to some value. All right, or I could go down. All right, there are cases where you oscillate, where you go up and then down and up and down. If you've taken trig, you've seen those, but we're not going to look at those in this course. Okay, then if I move to the left forever, I could either go up, I could maybe level off to some value, or I could go down. Alright, so those are going to be the 6 cases we're going to look at. Now what's tough is getting the notation right. So let's flip back over here. Alright, if you level off to some particular value, okay, the notation that we're using here is an L to be a constant, but this is going to be when we level off to a number. Alright, and we'll talk about how to find that number in a second. Okay, if we go up, then we're saying the output is shooting up to infinity. Okay, if we're going down, then we would use negative infinity. Alright, now what makes this tougher though is that we also have an infinity underneath the limit symbol. Okay, this piece right here tells me whether I'm going to the left or the right. Okay, so that's what this piece does. Okay, so I could either go to the left, to the right, I could either shoot up, shoot down, or level off. So there should be 6 cases which I drew over here. Alright, so let's see if we can get the notation here. For these 3 on the left, I'm going to the left. So this would be the limit as x approaches negative infinity of f of x. Okay, so this part underneath the limit is what tells me left because it says negative infinity. Similarly, this is the limit as x approaches negative infinity of f of x, and the limit as x approaches negative infinity of f of x. Okay, so the stuff underneath the limit, this negative infinity over here, is what tells me that we are going to the left. Okay, now the stuff on the right hand side of the equal symbol tells me whether I am leveling off, going up, or going down. So in this case I'm going up, so this would be positive infinity. Okay, this case I'm leveling off to some number. We'd put that number there. I'm just going to use the generic L here. And if we're going down, this would be negative infinity. Okay, so the concept's not tough. What's tough is figuring out what infinity means depending on where you are. Okay, so for example, here below the limit is telling me left or right, but on the right hand side of the equal sign is telling me whether we're going up or down. So let's see if we can do the same thing over here. This would be the limit as x approaches positive infinity, because I'm going to the right, and that's going to equal positive infinity because I'm going up. Okay, this case over here, the limit as x approaches positive infinity, because we're going to the right, of f of x. Well, this is the case where we're leveling off to some number, and I would write that number over here. Okay, and then over here, the limit as x approaches positive infinity, because I'm going to the right, of f of x. Well, now I'm going down, so I'm going to use negative infinity over there. Alright, so I hope those 6 cases of the end behavior kind of help clarify this. Again, the concepts aren't tough. What's tough is getting the notation right. Okay, now in this course, we're only going to determine end behavior graphically when I give you the picture, or numerically from the equation. So we'll do an example of this, but this will be when you want to use your table menu to see whether your outputs are getting really big, really small, or leveling off. Alright, so let's look at an example. Okay, here we have a function c of t, which tells us the number of million credit card holders t years after 2000. Alright, let's go ahead and enter this in our calculator, because I know we're going to need it here in a second. Alright, so if you guys are still getting used to this calculator, we're going to first hit the menu button to get to the main menu. Now this simulator I'm using is slightly different in the menu choices, but the keystrokes are going to be the same for you. So I'm going to choose my graph menu. Okay, I have some old stuff in here I want to delete. So I hit F2 to delete, and then it says, are you sure? Yep, F1. Delete F1. Alright, now I'm going to enter my equation, and we spoke about this in class, but what is important here with the logistic function, you probably don't know the name of this function yet, but we'll talk about it in section 110. If you have a fraction, I need parentheses around my numerator and denominator. Now the numerator is just one thing, so that's not going to be too tough. But I'm also going to need parentheses around my exponent when I enter this into the calculator. Alright, so let's see if we can do this. We want 29 divided by, open the parentheses for the denominator, 1 plus 18. Now that e is not a variable, it's a special number, and if you can see it right here in yellow above natural log, so to get anything in yellow you need to hit shift first, shift natural log to get the e, and then open the parentheses to begin your exponent. Okay, this is negative 0.43, and we're going to use the x theta t button for our input variable always. Then I'm going to close the parentheses to end my exponent, but then I need to close them again to end my denominator, plus 158. Alright, so here we are given a domain in the problem, which is going to make things a little easier. So here I am interested in years 0 years after 2000 to 15 years after 2000. So that's going to help me with my viewing window. So again, the viewing window is in yellow up here above F3. So first I have to hit shift F3. Okay, I'm going to give the calculator the x minimum of 0 and the x maximum of 15. Okay, now we're going to use the zoom auto feature to get the calculator to pick the range. So I'm going to choose execute to save that, then F6 to draw, and I don't see much going on here because my window is pretty bad. So do you see zoom is in yellow above F2, so I hit shift F2 to zoom and then F6 for the auto. Alright, now we get a graph very similar to what we see here in the note-taking guide. Alright, so the first thing we want to do is talk about concavity. Alright, so from 0 to A, alright, so that would be here. We're just estimating this point A here yet because we don't know how to find that exactly yet. We want to talk about whether we're increasing, decreasing, concave up, or concave down. Alright, so my first interval is going to be 0 to whatever this number A is that we're not sure of yet. Okay, so as I move left to right, I'm going up. So this is going to be increasing. Okay, now if I take 2 points and connect them in this interval, that is above my curve, so we are concave up. Okay, so let's see if we can do the same thing from our next interval. So from A to 15, all right, if I move left to right, I'm going uphill, so this is increasing. All right, and then if I take 2 points in this interval and I connect them, that line is below my curve. So this is going to be concave down. Okay, so in the next question it says, how does the behavior of C change at this point A? All right, well, I'm increasing the whole time. We saw that just a second ago. So the direction doesn't change, but do you see the concavity changes? So here the concavity changes at this point A. Okay, and the mathematical notation that we just learned, or name, for a point where the concavity changes is called an inflection point. Alright, so we have an inflection point at this input value of A. Now, we want to figure out what these limits are. Now let's go back to the graph we were just looking at here. You might be able to look at the graph and say, okay, if I go to the left forever, maybe that's going to level off, maybe it goes down. If I go to the right forever, maybe that levels off to some value, maybe it keeps going up more and more slowly. So we're going to use a numerical approach to figure this out. Alright, so I've got my function in the calculator, okay, and what I want to do is I want to give it larger and larger input values, okay, and try to determine whether the output values are going up, leveling off, or going down. Alright, so I'm going to use the table menu to help me with that. So I'm going to hit menu, and I'm going to go to my table menu. Alright, the equation is already there. Now, I'm just going to view my table with F6 and then type over whatever input values are there to give it the 10, 30, 90, 270, 810. Alright, so my default here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I'm just going to type over these values. Alright, so I want to give it 10, 30, 90, 270, and 810. Alright, so let's come over here and look and see what's going on with my output. So at 10, I am at 181.308. 30. If I round to 3 decimal places, that would be 186.999. Alright, then at 90, I'm 187, 187 again at 270, 187. Alright, so looking at these output values, it appears that when I go to the right forever, I'm going to level off to this value 187. Okay, now we want to do the same thing going to the left. Alright, so if I go to the left, I am going to enter these values of negative 40, alright, negative 80, and negative 120. Alright, so it looks pretty clear that this is getting, I have 158.000, 158, 158. So if I rounded to 3 decimal places, I should get 158, 158, and 158. Alright, so when I'm going to the left, that's what this notation says. When I go to the left here, I'm leveling off to 158, and when I go to the right here, I'm getting really close to 187. Alright, so now I think what we are asked next is to use this mathematical notation. Yes, alright, so to write this notation here, I'm going to say the limit. Now what goes under the limit tells me left or right, so let's do left first. As t approaches negative infinity, okay, the name of the function is c of t. So this is read, the limit as t approaches negative infinity of c of t equals, well, that was when we went to the left. Now when we went to the left, if we remember that we got really close to 158. Okay, so this value is going to be 158. Okay, now let's do the same thing to the right. So I'm going to write the limit as t approaches positive infinity, so the infinity underneath the limit sign says I'm going to the right, of c of t equals, and I believe that value was 187. Okay, now if these numbers kept getting larger and larger and larger, that would be positive infinity, or if they kept getting smaller and smaller and smaller, that would be negative infinity. We don't have an example like this in the note-taking guide, but you will absolutely see one in the WebAssign homework. Alright, so we want to write the equations of the two horizontal asymptotes. Alright, horizontal asymptotes. These are going to be imaginary lines which we get really, really close to. So if I were to draw this, here's my axes. Alright, this stuff that I am drawing in red here is the actual function here. Levels off and then it levels off again. Alright, now the asymptote is not part of my graph, but we oftentimes draw these imaginary horizontal lines to show what the end behavior is doing. So this stuff in green is not actually part of the graph. It's just a line that we would get really, really close to. Alright, so for a horizontal line, that would equal a y value. Okay, one of these horizontal lines is at 158, and the other one is at 187. Okay, so what might not be obvious is an asymptote will not be drawn as part of the graph. It's just to help us understand what the end behavior is doing. Alright, so in the last example we found those limits numerically using the table menu. In the next couple examples, we're going to find them graphically just by looking at the picture here. Alright, so understanding this notation here. Alright, so this notation here, the thing underneath the limit sign tells me left or right. So negative infinity would be to the left. So if I go to the left, 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 this is heading upwards. So to represent upwards, I'm going to use a positive infinity. Okay, over here in the next one, this tells me I'm going to the right. So if I go to the right here, I'm going down, so that would be negative infinity. Okay, now we want to know the number of horizontal asymptotes. Well, that would be in the case where we level off, so we don't have any here, so I'm going to put 0. Okay, so in this next example, underneath the limit sign, I have a negative infinity, so that says left. Alright, now when I go to the left, do you see how that levels off there at about 0? So my result here is going to be a number 0. Okay, then when we go, x goes towards positive infinity. When I go to the right, I'm going up, so that would be positive infinity. Okay, in this next example, again, underneath the limit, this is saying left, so when I go to the left, I'm going down, so that would be negative infinity. And then this piece tells me right. When I go to the right, I'm also going down, so that would also be negative infinity. Okay, then in this case, we don't have a left-hand limit because we have this asymptote here. So here, if I go to the right forever, I am going up, so that would be positive infinity. All right, now I forgot to answer this question over here on the left. The number of horizontal asymptotes, that would be 0 here. Now let's come back here. The number of horizontal asymptotes. This might be tricky. This equation has a vertical asymptote. This is this dotted line I'm drawing here at 0. Alright, but it didn't ask me about vertical, it just wanted horizontal. So there are no horizontal asymptotes, so I'm going to put a 0 there. Alright, and lastly here, if I go to the left, this is saying left, I'm getting really, really, really close to this L here, so I'm going to put that number. Okay, when I go to the right, it's getting really, really close to the x-axis, which would be a value of 0. Okay, now how many horizontal asymptotes do we have? Now one is quite obvious because this little dotted line that they drew for us is one of them. But you see there's another one here at 0. So this one is going to have 2 horizontal asymptotes. Alright, and lastly, when I go to the left for this function here, I'm going down. So that would be negative infinity. And when I go to the right here, I'm going up. So that would be positive infinity. Right? There are no limiting values, so I have 0 horizontal asymptotes.